record on this computer. Now it's being recorded. Great. So let me start over again fairly quickly at the beginning. So let's start the lecture. And here are some logistics. I'd like to talk about these topological methods, a discussion section later today. And now I'd like to wrap up discussion of perturbation theory anomalies. So we had this the surprising result that certain integral of the gauge theory always need to be an integer so that it qualifies as a topological invariant. And so what I'd like to show you now is why that is true, rather independent of the boundary conditions. And so this integral is defined only on closed spaces, namely the spaces without boundary. And one example of such a closed space is this the rectangle, the periodic boundary condition, so or torus, if you like. So these two arrows are meant to be identified. These two double arrows are meant to be identified. So this defines a rectangle of area Lx, Ly. So this is one example of space without a boundary. So the question is there any reason why the magnetic field that goes through this rectangle has to be quantized such that this integral is integer? So in order to, yes.
Sorry, can I ask a quick question?
Go ahead, Nick.
So when you say a closed space, does it also have to be compact?
Yeah, I'm imagining compact space, yes.
Oh, okay.
Is there any non-compact space that is closed without boundary? Or I guess infinity is not supposed to be boundary.
Yeah, so if you were just speaking of the boundary, then if we just had an infinite plane, it wouldn't have a boundary, but it would be
fair point. Fair point, yeah. So in order to make everything well-defined from a mathematical point of view, I'm talking about a closed space without a boundary, which is finite and therefore compact. That's right. So thank you for asking that question. So on this rectangle, I can have this vector potential that reproduces the constant magnetic field. But now that the vector potential explicitly depends on x, this is manifestly not periodic along the x direction. So when I shift by Lx along x direction, then I need to perform a gauge transformation at the edge of this rectangle, so that the vector potential goes back to the original form, namely that at this right-hand side of this rectangle, then the vector potential becomes B0Lx. So I need to find a way of doing a gauge transformation so that AY changes by negative BLx, so that the vector potential returns to the original form at left-hand side of this rectangle. And indeed, I can find such a the gauge transformation. So I need to find this phase factor e to the IE theta by writing this. I don't know why I wrote e to the IE theta twice. So e to the IE BLxy. So if I take this gauge transformation, y derivative would picks up EBLx from the exponent, and E is cancelled by this 1 over E up front, so that I can achieve the desired form of the gauge transformation. But this gauge transformation is supposed to be defined along this right-handed side of the rectangle, and namely that this also needs to satisfy periodicity in the y direction, because this bottom edge and the top edge are supposed to be identified. What that means is that when y changes by Ly, then the phase has to be multiples of 2 pi. So what appears in the exponent then is EBLx times Ly. That has to be 2 pi n. And this is precisely the quantization condition we talked about, because EB and Lx is the spatial integral, divided by 2n is n, which is an integer. So this is exactly an example where the integral of the gauge field has to be in an integer because of the consistency of the gauge transformations acting on this periodic space. So this is one, I emphasize, this is one example where I can explicitly demonstrate why this integral has to be an integer but it's independent of this particular choice of space, because on the next slide, I'd like to show you how it works on actually sphere instead of a torus. But anyway, any questions about this? And this problem here is identical to the problem of the Landau levels in quantum matter physics, where you like to work out the energy levels of the point particle in a constant magnetic field. And so even for the Landau levels, the area integral of the magnetic field has to be quantized. And this integer n actually turns out to be the multiplicity of the states in the lowest Landau level. So n really has to be an integer because it counts the number of states, and which is in the direct correspondence to this Atiyah single index theorem I mentioned on the previous slide. And there is a lecture note named landau.pdf on B courses, so I encourage you to look at that. Anyway, any questions about this? Go ahead.
Is there a generalization of this to four-dimensional space-time?
I will talk about that later.
Okay.
Thanks for asking. And I also need to emphasize that because this is a topological invariant, I worked it out for the case of the constant magnetic field. But even if the magnetic field is a little bit bumpy inside, and this statement should not change because it's not subject to the continuous variation when an integer cannot jump by the continuous variation. So even if we have rather random magnetic field inside, this statement that this integral has to be integer still remains. So that's the sort of the strength of the argument based on topology, because especially in the case of quantum matter physics, your system is never this clean. The free space with constant magnetic field, there are all kinds of impurities inside. Magnetic field may not be uniform, but still the end result is supposed to be true. And that is one example of how strong an argument based on topology actually is. So on the next slide, I'd like to show the same situation in the case of a sphere instead of on a torus. And when you actually surround a space with a sphere and you're talking about the surface of the sphere, S2, you are imagining that there's some magnetic source at the origin. And the magnetic source means it's a magnetic monopole. And this discussion actually goes all the way back to Dirac, that the magnetic monopole charge also needs to be quantized. And what I'm showing here is sort of the modern argument based on the paper by Witten. What you can do is to first write a point particle action. And the point particle action is given by this coupling of the vector potential to the velocity of the particle. And what you notice here is that the velocity times the time integral, which you have to do in order to define an action, is that dt cancels. So this point particle action in the presence of the vector potential turns into a line integral of the vector potential. And the place where you might have come across this is when you have seen the discussion of Harlan-Bohm effect. So when you actually surround a solenoid with a constant magnetic field inside, then the wave function picks up the phase according to this line integral. So even where you are in space where the magnetic field doesn't exist, the vector potential does exist, and you pick up this line integral for a quantum mechanical wave function, and therefore you actually change the interference pattern, and that's the Harlan-Bohm effect. So the fact that the point particle action is actually a line integral of the vector potential, I believe we have seen elsewhere before. So what I'd like to do is to apply this form of the point particle action on the surface of the sphere. So what I'm talking about is that there is a magnetic monopole at the origin, and you have a particle that is actually confined on the surface of the sphere. You can only move on this surface. And then if you are, for example, thinking about the partition function or something, you can consider a closed loop on this surface. And the closed loop integral can be rewritten in terms of the surface integral using Stokes theorem. So here I have this contour gamma, and I integrate the vector potential along this loop. And using the Stokes theorem, I can rewrite this loop integral in terms of an area integral over this area, the shaded area D, and that's the first expression over here. But there's another way of using Stokes' theorem where I can define the area integral to be sort of the opposite side of this sphere, which is the shaded region D prime. And you have to be paying attention to the orientation of the surface. So if you actually work it out, then there's a negative sign times this area integral on this the complement of the surface of sphere, which is D prime. So I have now an ambiguity in writing this loop integral of the vector potential either in this form of the area integral or in the second form of the area integral. And that sounds really strange because then your action is ambiguous. But then you remember that this action is supposed to be inside the path integral in quantum theory, so that the action actually goes into the exponent with I times I over h bar. So even though the action itself may be ambiguous, as long as the ambiguity is 1 when you actually put it into the exponent, that's allowed. And in fact, the amount of ambiguity, namely difference of the action, depending on which way you write it, is this one minus that one. So the amount of ambiguity, delta S interaction, is the sum of this integral and this area integral, which is the integral over the entire surface of the sphere. That's this expression here. And if the magnetic charge of the monopole at the origin is G, then this area integral would be 4 pi G, because you integrate the magnetic flux for the entire sphere over the solid angle 4 pi. So what then you find in the exponent is I over h bar 4 pi Eg. So as long as this combination is the multiple of 2 pi I, then path integral is single valued, even though the classical Lagrangian is not. So that gives me this quantization condition, the 4 pi Eg is 2 pi h bar n. And this is what Dirac discovered a long time ago. So it turns out that if there were, of course we haven't discovered one, but if there were a magnetic monopole somewhere in the universe, then the existence of such a magnetic monopole implies that you always have to satisfy this condition. So, there's an even speculation that such a condition is the reason why the hydrogen atom is neutral. So if you think about it, hydrogen atoms are neutral because you're adding the electric charge of electron and the electric charge of proton, and they exactly cancel against each other, even though they're made of different things. The proton is made of 2 up quarks and 1 down quark, and up quark has charge 2/3 E, and down quark has charge minus 1/3 E. 2/3 plus 2/3 minus 1/3 is 1, and that's how this ends up being 0. But as I said, it's made of totally different things. So why is the condition that they have to be exactly cancel against each other? So the one possible answer to this is that if there were even just one magnetic monopole in the entire universe, you're supposed to satisfy this condition, and therefore electric charge of particles should always come in the quantized unit, so that there's no way that the electric charge of electron and proton charge and electric charge of proton may not cancel at the level of 10 to the minus 23 or something. And that is actually the experimental limit on what the charge of the hydrogen atom could be if it's finite, because that's roughly, you collect Avogadro number of hydrogen to measure the total charge of the system. So it has to be as accurate as 10 to the minus 23. But if the electric charge is supposed to be quantized because of the topological reason, then no wonder the charges do cancel exactly. So that's one possible speculation that Dirac came up with. But for the purpose of our discussion here, that this is yet another example that E times area integral of the magnetic field is again indeed quantized in integer multiples. And so this expression here, I managed to recover h bar because I just remember the path integral comes with an h bar. I didn't have this h bar on a previous slide. But anyway, so this is the same condition we talked about on a previous slide, namely that the area integral of the magnetic field, which is the first Chern class according to the language of fiber bundle, has to be an integer. And this is the way you can actually derive the result based on this very simple conservation. And it's a beautiful argument by Edward Witten. Any questions about this? It's okay. It's getting more convincing. At least this is a demonstration that torus and a sphere would lead to the same conclusion about the quantization of the total magnetic flux punching through that area. And we go back and talk about four-dimensional case later on. Okay. So, so we talked about how we can compute this the amount of the change in chiral charge by using the Jacobian in the path integral. And so what I have done explicitly is a calculation when the space-time is 1 + 1 dimensional, but you can extend it to arbitrary dimensions. And so in that case, gamma 5 also needs to be this the antisymmetric product of all gamma matrices up to 2n dimensions. And I'm specifically talking about even dimensions here, where gamma 5 can be defined. And then you go through the same exercise of writing this Dirac operator squared in terms of just covariant derivative squared plus a piece which goes with sigma mu nu f mu nu. And here's a typo, there shouldn't be factor of t here. Sorry about that. And it's supposed to be e squared instead. And so what you do then is to expand the sigma mu nu f mu nu down from the exponent to the extent that the product of sigma mu nu's exactly cancel gamma 5 factor. So if you remember what I told you a long time ago, that trace of gamma matrices is the same thing as the Wick contraction of the gamma matrices. So gamma 5 have every gamma matrix multiplied. So I have to find its partner to do the Wick contraction for every gamma matrix inside gamma 5. So gamma 5 is a product of 2n gamma matrices. Sigma mu nu is a product of 2 gamma matrices. So I need to bring in n factors sigma mu nu to allow for the Wick contraction of every gamma matrices so that I can get a non-zero trace. Hence, I need to have this n power here. And then I contract gamma 5 with sigma mu nu's. That turns into this Leibniz-Witte symbol. And then I have n powers of f mu nu as a result. And when you do this, it turns out that the factor of t I get from the exponent is t to the n, gets precisely canceled by the momentum integral of this Gaussian factor, which is pi over t to the nth power, so that I can safely take the limit of t going to 0. And the end result is this. So for any arbitrary even dimensions, you do have chiral anomaly, which is given by this expression here. And the compact way of writing it is in terms of the differential form. F mu nu is a 2 form. You just put in an exponent. And when you take the first power of f, that's the expression we have talked about in terms of this Landau levels and magnetic monopole on the previous slides. If you want to have a 4-dimensional case, then I take 2 powers of f. And so this is the expression that can be used for arbitrary even dimensions. And this is what is called the Chern character. So for any closed compact space of arbitrary 2n dimensions, the integral of this combination is always supposed to be integer, which is a surprising statement about the nature of the gauge field, but this has to be true based on this argument that the number of change of the particle due to chiral anomaly always needs to be an integer because it's number of particles. Okay, any questions about this slide? Now I notice multiple typos. I left out this parameter alpha for the last 2 lines, so I'll fix that later. Okay.
Sorry, which Chern class were you talking about?
So this is the Chern class, sometimes also called CH.
Oh, so I heard that there's different like first Chern class, second Chern class?
So it's just a power series expansion of this. The first Chern class is the first power in f over 2 pi. Second Chern class is f over 2 pi squared over 2 factorial.
Okay.
You just do the Taylor series expansion of this, and you pick up the first power in it, second power in it, third power in it. So they are C1, C2, C3.
Okay, thank you.
Okay. All right. So what I very quickly told you last time is that the anomaly is actually very strange, surprising, is even shocking, and people were indeed shocked. That's why it was named anomaly, but it's actually a good thing. And the one example I have given you is this apparent absence of the 9th number Goldstone boson in the theory of strong interaction QCD. So I've given you some evidence that it is consistent to interpret some of these, what is called the pseudoscalar mesons in the strong interactions, which are the bound states of quark and antiquark, can be interpreted as a number Goldstone boson of the spontaneous symmetry breaking of UNF left cross UNF right chiral symmetry. And we talked about this for general NF and NC, I think, last week. But if this is the picture, then you're supposed to have 9 number Goldstone bosons because UNF, U3 is 9-dimensional group, but there seems to be only 8 of them in the experimental data, and that was the puzzle. So the way we can explain it now is, well, you thought that there was this U3 equals U3 symmetry in the classical Lagrangian, but the quantum mechanically, there is this anomaly effect. So U1 part of this U3 equals U3 was not a symmetry to begin with. So the true symmetry is only SU3 equals SU3, breaking to SU3, diagonal subgroup, and therefore you only expect 8 number Goldstone bosons. SU3 is 3 squared minus 1, 8-dimensional group, and therefore that's the way you want to see 8 number Goldstone bosons, but not 9. So that's the way we now understand what's going on in strong interaction indeed. So in the case of 4-dimensional space-time, then the anomaly comes from this triangle diagram. Remember, in 1 plus 1 dimensional QED, we computed the 2-point function, which was related to vacuum polarization diagram. But in 4D, this is actually a triangle diagram. So you use gamma mu, gamma 5 here, and contract that with the external momentum Q mu. And you have 2 vertices, which couple to gauge fields. That's why you have 2 powers of gauge fields. And so this is the expression for the chiral anomaly in 4 dimensions when it's coupled to QED. And in the case of QCD, the only thing you need to change is that this gauge boson is now a gluon instead of photon. And it comes with, of course, the matrix TA, one of the generators here. So in the case of the 3-flavor QCD, where we have up, down, and strange quarks as like quark species, and to the extent we ignore their masses, classically, this axial current is supposed to be conserved. But as we said over and over again, quantum mechanically, there's this anomaly so that this current is no longer conserved. The amount of non-conservation is given by this expression, where F mu nu A is the gluon field strength. And it's multiplied by NF, which is 3 in this case, because you have to add 3 triangle diagrams on top of each other. So that's why there is no U3 equals U3 symmetry in this theory. To begin with, the only symmetry is SU3 equals SU3. When you take U1 part of a U3 and choose the left and right transformation the same, that means that you are changing the phase of all quark species by the same amount, and that's nothing but the baryon number symmetry. So that is still there. But the U1 phase transformation of letting the left-handed and right-handed fields are changed oppositely is the symmetry that's reflected by this chiral, the axial current, and that symmetry is now gone. So it just doesn't exist. So there's no U1 problem. So absence of 9th Goldstone boson is not a surprise anymore because there was no symmetry to begin with. So this is how anomaly actually helps us to understand the real-world physics of the SU3 gauge theory, namely QCD. And not only that, there used to be another puzzle, how pi naught can ever decay. And pi naught is the bound state of up quark and anti-up quark, and down quark and anti-down quark, with a relative minus sign in the wave function, so that this is actually isospin triplet particle. And again, you can define this axial current, and as long as this axial current is conserved, people could show that pi naught would not decay. But experimentally, it does decay fairly quickly within a lifetime of like 10 to the minus 16 seconds or so. So you need to understand this. And it turns out that this current, again, is not conserved, because if you actually put that into this triangle diagram, you compute a diagram with up quark inside the loop, then you pick up quark charges twice, that's 2/3 squared. Here is the minus sign, it's a minus sign. And you pick up the triangle diagram with the down quark, so you pick up the down quark charges twice. And the quarks come in the multiplicity of number of colors, that's 3. So you expect that this divergence of the axial current is given by this expression. And the amazing thing here is that, well, you may not trust this result because these are quarks running inside the loop. They are coupling to gluons with this very strong coupling constant, which even diverges at low energies. So how can you ever trust this kind of calculation? But again, because of the fact that this is supposed to be topologically invariant, it's actually immune to any perturbative corrections from the gluon exchange inside this triangle. And I mentioned that Aller and Bardeen actually noticed this first, and they have shown the absence of corrections based on brute force diagrammatic arguments. But now we have better understanding that this is based on topological invariance of this quantity. So you do trust this result, even though it's subject to strong interactions. And then that would allow you to compute the lifetime of the pi naught because of this anomaly, and that agrees with experimental data beautifully. So anomaly is supposed to be a good thing, at least to the extent we talked about. All right, so this is the sort of repeating what I discussed on Tuesday, but because I went very fast towards the end, I tried to make it a little bit more, hopefully, comprehensive and understandable. So any questions about discussion so far?
Okay, I'll just go. So wait, does the anomaly give you a relationship between the coupling renormalization and the field strength renormalization then for the gauge field?
So then you're talking about, you would like to relate this, what we call FF dual. So F dual is the epsilon tensor times F over 2. So FF dual and FF somehow needs to be connected if you like to talk about the coupling, the running coupling constant. Mm-hmm. And that relationship doesn't exist in the standard gauge theory. But it does exist when you're talking about the supersymmetric gauge theory, because FF and FF dual happens to be in the same multiplet under supersymmetry. So that's when you do expect some relationship between them. And that's the paper I actually uploaded on B courses I wrote with Nima some time ago. So in the case of supersymmetric gauge theories, you can really relate this chiral anomaly, which is exact, to the beta function of the running coupling constant, so that you can actually gain information about certain exact results on the running coupling constant.
Okay, so this is, yeah. So that's actually the same question I asked yesterday. I didn't realize I asked the same question.
Right.
Okay, yeah. I see. Okay, thanks.
Okay, any other questions here?
Yeah, I have a question about this U1 problem from the beginning. So, so this chiral symmetry would be broken if we included the masses of these quarks, right?
Right, that's right.
So why are we surprised that a symmetry that we're inventing by treating them as massless is broken, when we know that it's not a symmetry to begin with?
Yeah, so that's a very good question. So the way we actually view the dynamics of QCD is that taking massless limit is a very good approximation. And we understand the QCD dynamics by perturbing the theory from the massless limit to the finite mass, which is much smaller compared to the scale where the gauge coupling constant blows up. So blowing up gauge coupling constant really dictates the main feature of the dynamics. And because the quark masses are smaller than that, then taking them to zero as a zero thought approximation is a good approximation. and you perturb the system by including these finite masses of quarks later on. And when you do so, you actually have a quantitative prediction that the mass squared of these number-Goldstone bosons, which are no longer true number-Goldstone bosons because symmetry is explicitly broken now, but because we are perturbing from the massless limit of the number-Goldstone bosons, you can say that the number-Goldstone boson mass squared should be turned on only to the extent proportional to how much you have broken the symmetry, which is namely the quark masses. And the meson have two quark ingredients inside, so the sum of two quarks is what gives you the mass squared of the number-Goldstone bosons. And that's something you can show by writing the theory called the chiral Lagrangian, which is just a description of the number-Goldstone bosons on this coset space of G mod H. And then you can figure out how exactly this perturbation would enter this chiral Lagrangian. And this is the consequence of that analysis. And here I'm demonstrating that this the proportionality between the number-Goldstone boson mass squared and some of the quark masses actually does work by looking at some of the meson masses. So this is how we believe that massless limit of the quarks is a good approximation. But in that limit, we did not see the ninth number-Goldstone boson. So because what could have been this ninth one is so heavy, which is even heavier than proton, which is a consequence of this strong dynamics. So considering this to be massless is clearly not a good approximation. So that's why the absence of the ninth number-Goldstone boson was a mystery to us, and now we understand it's a consequence of anomaly. Does that answer your question, Nick?
Yeah, I think so.
Okay.
Yeah, I guess I'm still a little confused on it seems like we did the calculation now for 2n dimensions and we're still getting the same result. So I guess it applies for our 4D spacetime. Does it, but we're still assuming that our spacetime is closed, which, I mean, should we take the fact that this is agreeing with experiment as suggestive that space-time is closed? Because to me, that would be the biggest surprise of all. Because we assume that topologically it's R across some 3 manifold that could be closed or open, but overall we assume it's non-compact.
So it doesn't lead to the conclusion space is closed because at the end of the day, QCD dynamics is gapped. So there are no massless particles. So all the correlation functions are short distance. Therefore, QCD should not know about the boundary conditions at infinity of space. It only has local information in its dynamics. So even though we can use the closed space as a way of making arguments and analyze the dynamics of theory, at the end of the day, the answer should not depend on the boundary conditions or whether the space-time is closed or open, because the dynamics is short-ranged. So it's sort of an intermediate step where you pretend the space-time may be closed in finite volume to get the non-trivial result we like. But at the end of the day, we believe that the end result doesn't depend on the choice of space-time. So the one sort of morale of this is that whenever you're facing a rather difficult problem in dealing with physics, you want to use whatever tool that's available to you. And making space-time small and finite volume, if that helps you in any way, you use it. But only to the extent that you believe that your end result doesn't depend on this particular tool you used. So that's a sort of very pragmatic approach to physics. And taking the massless limit of quarks is yet another example. And certainly quarks are not massless. Chiral symmetry is not exact. But pretending that the quarks are massless turns out to be a very good approximation to the real world. Then you use that as a tool. Again, to the extent that end result doesn't depend on the particular zeroth order approximation you took. Does that make
see.
sense?
Yeah. Yeah, I think I have an idea of it. I mean, I think to really understand it, I need to spend more time and get into more detail. But I think I have a vague idea.
All right, sounds good. Okay, so that's how anomaly actually helps.
Sorry, I have another quick question. So is
Go ahead.
what actually ends up setting the scale, mass scale of the big meson?
Yeah,
Is it
so
related to the axial
this is
current
this
thing?
formula here. Yeah, so the meson mass squared is the consequence of how much chiral symmetry is broken, because if it's not broken, then they are supposed to be exactly massless number Gaussian bosons. So the axial current, when you use this the correspondence between the meson state and the spontaneous broken symmetry, the axial current is roughly speaking the gradient of the meson field. So when you take a divergence of it, the gradient of the meson and divergence becomes just a box on a meson field, which is mass squared. So that's how you find mass squared.
Okay.
On
So
the other hand, in the quark language, how much axial current is not conserved is proportional to quark masses. So you're comparing two different languages of describing the same thing. If you use a meson language, non-conservation of axial current is proportional to meson mass squared. If you use the quark language, non-conservation of axial current is proportional to quark masses linearly. And dimensional analysis suggests the only other mass dimension you can use to make them equal is to use this confinement scale lambda. So that's how you arrive at the conclusion that the meson mass squared is proportional to quark mass times the confinement scale.
Right, but is the mass of eta prime set by the anomalous axial current?
So eta prime mass is of the order of lambda squared instead.
Okay.
So that's there even when you take the quark mass to 0.
Oh, okay. Yeah, okay. Thank you.
Okay, thanks for the question. So the anomaly actually helps us to understand certain aspects of physics. And we also try to apply this consequence anomaly in the quantum Hall effect in discussion section later today. So anomaly is actually helpful in getting certain very important results in physics. So what I haven't told you yet is that now I have this expression for the chiral anomaly in 4 dimensions. I emphasize that this also has to integrate to integer. Do we understand that? Purely in 4-dimensional point of view, we talked about this 1 + 1 dimension where you could really see the level changes and stuff like this. And in 4 dimensions, it's a little bit more complicated, but nonetheless, there's a way of actually understanding it. So the first step is to rewrite this chiral anomaly as a total derivative of something called Chern-Simons term. And it's always true that in any 2n dimensions, this kind of the Chern class or the chiral anomaly is a divergence of the Chern-Simons term. It's always a total derivative. So because this total derivative is supposed to be the divergence of the axial current, the first thing you notice is that if you take the difference between the two, the original axial current minus this Chern-Simon, this whole thing is divergence-less. So you might say, okay, but there's still a conserved current. What's the big deal of the anomaly? Symmetry is not broken. Well, it is broken because this new conserved current is not gauge invariant. This Chern-Simons term actually changes under gauge transformation. And it turns out that under infinitesimal gauge transformation, this Chern-Simons current changes only by a total derivative. So it really doesn't affect much if you, for example, try to define a charge using the time component integrated with space. And if you drop the boundary terms, then this still looks like gauge invariant. But there are special gauge transformations you can perform on them, which actually makes this integral of this Chern-Simons term also change. So again, in response to Nick's question, that we pick whatever is convenient for us for the purpose of discussions and hope for the best that the answer doesn't depend on that. And so there is actually a non-trivial gauge transformation you can perform on the 3-dimensional sphere. And that's very much analogous to what we have done in 1 + 1 dimensional QED, where the initial state and final state differed by a gauge transformation that winds around this one-dimensional space once. So that was what I call the homotopy group, which corresponds to a gauge transformation, which is nothing but a map from one-dimensional circle, which is space, to one-dimensional circle, that is the U1 gauge group. In the same way, if you regard our space to be three-dimensional sphere, for the convenience of argument, you should look into whether there are non-trivial maps from S3, which is space, into the gauge group G. And this is a theorem due to Poincaré that every simple compact Lie groups has such a non-trivial map that the three-dimensional sphere can be mapped into the gauge group, which winds around in a non-trivial way. And you can count the winding numbers, which are integers. And the easiest example is SU2, which is actually S3 itself. SU2 has three generators. It's a three-dimensional group. It's a 2x2 unitary matrix with one unit determinant, which actually is the same space as the three-dimensional sphere. And I'll tell you an explicit form later on. So the map from three-dimensional sphere as a space into the gauge group SU2, which is also three-dimensional sphere, is really the wrapping, sort of the peeling off the orange and then try to wrap the peel on top of another orange so that you can count the winding numbers that way. So this is the way you can see that the gauge transformation can be topologically non-trivial. And under that kind of gauge transformation, it turns out that this Chern-Simons term changes by the winding number of the gauge transformation. And that's why this axial current doesn't lead to gauge invariant conservation law. So this is in exact analog to what we discussed in 1+1 dimension, namely that you have this topologically non-trivial gauge transformation that can change the gauge field. And in 1D case, it was just a constant piece of the vector potential. Here in 3 dimension, all the vector potentials come back in full glory, so it's a little bit more complicated. But it turns out that this really does change by an integer. And so that corresponds to how much the chiral charge changes from infinite past to infinite future when you gradually turn on the gauge field in such a way that the initial gauge field and final gauge field are related by this topologically non-trivial gauge transformation. And here are Chern-Simons. This is the Xin-Chen Chern. As I said, that he was a mathematician in math department in Berkeley. I was wrong. I thought he was a field medalist, but he wasn't. He received many other prestigious awards, but not the Fields Medal. But anyway, so he trained many excellent mathematicians, including Xin-Tao Yao, who did receive the Fields Medal. And Yao, you might have heard of the Calabi-Yao manifold that appears in string theory, and that Yao was a student of Chern. And James Simons was another student, and he was successful and even became the chair of the department at the math department in Stony Brook. But on one day, he decided to go to Wall Street. He was a pioneer in hedge funds, and now his net worth is $21.6 billion as of the October last year. Well, stocks plummeted because of coronavirus, so maybe it's lower now, but still is a billionaire. And he has been actually donating a lot of money. For example, Berkeley, the Data Science Center is named after him because he made a lot of donation to that. So this is James Simons, and James Simons and Chern is the one who really came up with this expression. Okay, so I hope that actually makes the connection to why there has to be certain integers associated with this gauge field in 4 dimensions. It's a little bit more explicit than what I used to be, and so that's and this is the final slide on that question. So as I said, this the difference between JMU5 and Chern-Simons is conserved, and here I'm giving you a very explicit form how this can change by an integer. So this particular element of SU2 gauge transformation is this non-trivial gauge transformation. So I put this sigma A xa over R in the exponent together with this R-dependent function f of R. And what you see first is that if f of r vanishes at the origin, then exponent vanishes, so u is 1 at the origin. I assume f at the spatial infinity is 1. So e to the pi I 1 times sigma xr is actually minus 1 as a diagonal matrix. So you can actually see it by really working out the Taylor series expansion of the exponent. And what if you notice that sigma a xa, if you square it, turns out to be just r squared because of this the anti-commutator of sigma a sigma b being 2 delta ab. So sigma a xa, when you actually square it, turns into just a number. So every even powers turns into numbers, and they add up to cosine. Every odd power is still a matrix, and they sum up to sine. And that's why how you can actually show this expression here. And when you go to the infinity, f of infinity is 1, sine pi of 1 is 0. So this second term vanishes. Cosine pi of 1 is minus 1. So this is the gauge transformation where u is 1 at the origin, and u becomes minus 1 at any direction you go to the spatial infinity. And because every direction spatial infinity is the same, you can regard the three-dimensional space to be three-dimensional sphere because you identify every direction at the infinity. And then how much this Chern-Simons changes under this gauge transformation, you can work it out to be given by this expression, given by the derivative of this matrix U. And you just explicitly plug that in here. And it turns out that this actually turns into a total derivative expression along the radial direction, so that I can write out this explicit expression along the radial direction. And if you take the boundary values, then this is just 1. Again, because sine 2 pi f vanishes, if r changes from 0 to 1, hence the result is 1. So this is the non-trivial gauge transformation with 1 unit of winding number. So as I said, this is rather similar to the case of one-dimensional QED, where you had this gauge transformation that winds around U1 integer times. And how many times you wind around corresponds to how much change there is in the number of right mover particles, number of left mover particles. And hence, the difference changes by 2, and that has to be an integer. And that's what we observed there. Here it's less explicit because I can't work out energy levels very in a compact fashion, but nonetheless, you do find the same fact that amount of change in J5 is given by amount of change in Chern-Simons, and the amount of change in Chern-Simons and the gauge transformation is given by this expression, which turns into this winding number of gauge transformation as an integer, and therefore, also in four-dimensional theory, number of change in the right-handed particles is +1, number of left-handed particle changes -1, and therefore the chiral charge does change by 2, which is always integer, which corresponds to this, how the winding number of the gauge transformation you do from infinite past to infinite future. So that's the precise correspondence between two-dimensional case and four-dimensional case, even though four-dimensional case admittedly is more complicated and less explicit, but this is as explicit I could make for the purpose of this discussion. Okay, any questions about this?
So when you say winding number, now that we're dealing with the higher dimensional case, I noticed a few slides back you had pi sub 3. So are we now talking about higher homotopy groups, not the fundamental group?
That's correct, okay. Yeah. So pi 3 refers to a map of three-dimensional sphere into some space, and you try to classify that map according to topological equivalence. So if a map can be continuously formed to another map, you consider to be the same. But if they are not continuously formable to each other, then that's considered to be a separate class. And if the map winds around in a non-trivial way, once, twice, 3 times, you can't continuously change from 1 to 2. So they are considered different classes, which is parameterized by the integer, which is the winding number.
Gotcha. Okay, yeah, I was a little confused because at first I thought it was Z mod 2 for the fundamental group of SU2.
Right.
I know so that if you go around twice, you get unbound.
So that's not true. Yeah. So this is not pi 1, but pi 3.
Yeah.
And because SU2 is a space which is equivalent to S3 itself, that map is S3 from S3 so that you can really sort of see why that it has to be counted by the winding numbers.
I see. Thanks.
Okay. So now that we see a process in 4-dimensional space-time where a number of particles can change, you can speculate. Maybe this has to do something with the origin of the asymmetry between matter and antimatter in the universe. And I don't go into details here, but there is a way of determining the asymmetry between matter and antimatter. First, observing the amount of deuterium in the universe relative to the amount of hydrogen, which you can do by looking at the absorption lines by the Lyman spectrum by the intermediate hydrogen gas, backlit by some bright object far away, such as quasars. And because the deuterium and hydrogen have basically exactly the same chemistry, but the reduced mass differs by at the level of 1 part in 4,000, because the mass of the hydrogen atom and the nucleus and deuterium nucleus is different by factor 2, while the mass of the electron is 2,000 times lighter than the proton. So the difference turns out to be only 1 part in 4,000. But with a modern spectrograph, you can actually pick that out difference. And what you see here is that there is a dip due to hydrogen Lyman absorption line. And there's a tiny dip on the shoulder, which is due to deuterium. And this plot by itself may not convince you, but you see the consistent pattern at all Lyman levels and also in different systems. So that's how you can measure the amount of deuterium in the universe today. And that's something you can compare to the prediction from the Big Bang. So when the universe started out, when the temperature was higher than about a 300 MeV, that's a confinement scale, quarks and gluons were liberated, which is in a state called the quark-gluon plasma. And when the temperature drops below that temperature, then the quarks and gluons become confined. Then you have a theory now system based on the protons and neutrons. But protons and neutrons still free. Only after temperature drops below 1 MeV, then the proton and neutrons start to come together and bind together to form a deuterium. And how much deuterium can be made that way depends on how many protons and neutrons you start out with. And that's how you can determine how many protons and neutrons there were at this early stage of the Big Bang. And that's this horizontal axis called the baryon to photon ratio. And so this deuterium measurement will tell you that baryon to photon ratio has to be within this magenta band. At the same time, the cosmic microwave background looks at the process, how the plasma of the nuclei and electrons became bound states into atoms, and so that the whole universe became neutral, and a photon could now freely travel, and that's how we can see this cosmic microwave background. And of course, the COBE, which was done by George Smoot in the department, really was the first one which could take a picture of the entire universe of the using cosmic microwave background. And so that process, how the electrons get bound together with the nuclei, depends on, again, the composition, whether it's only strictly proton or there's some admixture of the helium in it. And deuterium is so small amount, so it doesn't really affect this recombination process, but helium does, because about a quarter of the mass in atoms is in helium. So that, again, allows you to extract the amount of helium at that stage. And that would, in turn, would allow you to also determine the baryon to entropy ratio. And so that is this the Sion band, and they beautifully agree with each other. So this is an agreement between two stages of the universe, when universe was only 1 second old versus when universe was 380,000 years old. So that agreement really convinces us that we know the baryon to photon ratio, which is just a notch below 1 part in a billionth. What that translates into in the earlier moments of the universe, when the universe was filled with this gas of quarks and antiquarks, is that when the universe was very hot, and presumably that started with inflation, then energy of the inflation turned into matter. But when energy turns into matter, it's always accompanied with the antimatter. And that's what we see from this Dirac equation of creating a hole by moving negative energy state to positive energy state. So you expect the universe started out with an equal amount of matter and antimatter. But if this were the case, then everything would be gone by now. So what you need is a process of reshuffling the balance by picking one antimatter out of billion and turning that into matter. And all billion of them annihilate with each other. But because there's now tiny imbalance, this got left over, and that is supposed to be us. So whether we can understand this as a microcausal mechanism of changing antimatter to matter is, really sort of billion-dollar, trillion-dollar question here. And the anomaly may actually have something to do with it. And it is actually believed that it does. And this is one example of that. So anyway, the anomaly might have saved us from complete annihilation. And that is done in the context of the neutrino physics. So we have discovered that neutrino has a finite mass. And the neutrino can obtain a mass if there were this right-handed neutrino state, which we haven't seen experimentally. So this is really a hypothesis. But if there were such a state, then it can couple to the Higgs boson in the same way as all the other elementary particles do to pick out the mass. But if that's the mechanism, then you might expect that the mass of the neutrino would be comparable to other fermion masses, and obviously they are not. So the one way to explain why neutrino mass is so small is by adding yet another mass term, specifically to the right-hand neutrino, because it doesn't couple to any of the standard model gauge groups, which is totally neutral under all the gauging interactions we are aware of. So because this has nothing to do with the gauge interaction, then this m, in principle, can be arbitrarily high. And as a result, the neutrino for every generation will come with this 2x2 matrix. This YV piece is supposed to come from the Higgs mechanism, which is the next subject we will talk about, the Higgs mechanism in the same way as all the other charged particles like electron and top quark. So you expect this mass to be rather large. On the other hand, this mass m is supposed to be very heavy. And that here 0, which is not allowed by gauge invariance, so it has to be strictly 0. So this is actually an interesting matrix because there's one big entry. So one of the eigenvalue is supposed to be of the order of big M. On the other hand, determinant is the square of this off-diagonal entry, YV squared. So the determinant is a product of two eigenvalues, one of which is big M. So the other eigenvalue then is supposed to be suppressed, which is YV squared over M. So that's this the cartoon of the seesaw. So if there were this the mass term coming from the Higgs mechanism YV, you would think that this is too heavy for neutrino mass. But then you bring in this very, very big mass M, which is big, then the seesaw goes the other way, and that's how this neutrino mass ends up being light. And that's the idea called seesaw mechanism. And this is possible only for neutrino because the right-handed counterpart will be completely neutral under any of the gauge transformations. And if you think about the fact that even the neutrino we have observed, that is the only electrically neutral elementary matter particle. So if there is any way of reshuffling the amount of matter and antimatter, then you cannot change electron to positron because that would violate the conservation of electrical charges. But for the neutrino, if neutrino turns into antineutrino, it doesn't violate conservation of electric charge. So that might be possible. So the idea is that this right-handed neutrino is very heavy, as heavy as maybe 10 to the 15 GeV or something. It's very heavy. And they are produced in the early universe only. We cannot create them by accelerators anymore. But once they are made in the early universe, they will eventually decay. And because this mass term is a Majorana mass of the right-handed neutrino, so if you just compute this diagram, you would predict that the right-handed neutrino would decay with a 50-50 probability into matter or antimatter. But when you have this one loop diagram and look at the interference between them, this one loop diagram can violate CP so that the decay rate of this heavy Wagner neutrino into matter versus antimatter can be now different given by the phases of these Yukawa couplings, so that when these heavy particles decay, it would implant small asymmetry between amount of neutrinos or leptons versus antineutrinos or anti-leptons. But of course, what we like to see is the difference between the number of quarks and antiquarks, so that we survived to date. So the question here is that when you actually create this imbalance between leptons, can you actually turn that into imbalance in quarks? And it turns out the answer is yes. So if you look at the current for the lepton number, it's anomalous, again, because of the triangle diagram. The amount of non-conservation is given by this SU2 gauge field in the standard model. But the quarks will be subject to the exact same triangle diagram. So the amount of non-conservation of the baryons and non-conservation leptons are given by the same quantity. So if you have lepton asymmetry implanted by this decay of the heavy Wagner neutrinos, then by using this anomaly, you can change the lepton number to produce baryon number. So again, pictorially, so in the universe, the W field is fluctuating all the time. So just like the cartoon we did for the 1+1 dimensional case, all these energy levels are going up and down the whole time. But when the fluctuation of W field becomes rather large, then it can go one step above, and then the one particle will stick up like this. So as a result, you can change the amount of lepton and amount of quarks for all three colors by the same number. And then the rest is just looking for the chemical equilibrium of this reaction. So in order to minimize free energy, having asymmetry only in lepton gives you higher free energy than compared to balancing lepton against baryon, so that they will sort of settle somewhere in the middle. And so it turns out that once you create a lepton asymmetry from the Wagner neutrino decay, you end up with this equilibrium where you have both baryon and lepton asymmetries at the end of the day with this 35:65 ratio approximately. So this is how we may have created the asymmetry between the number of quarks and antiquarks before the QCD phase transition. And pretty much all of them have annihilated away, but there is one part in a billion that's got left over, and that's why you are here today. So anomaly is considered to be very important whenever we talk about the origin of this baryon asymmetry of the universe, because it is the only reaction we know that can change the amount of baryon numbers in a standard model. And this is the way you can use it for the purpose of explaining why we could survive the Big Bang. So this is the side story, but this is a fascinating story, I believe. And any questions about this? I heard a deep sigh. Who was that?
I'm not sure that I really understood the argument for how the lepton asymmetry can get converted to the baryon asymmetry, but maybe I need to read something more slowly if there's a good note on it.
Yeah. So at least mathematically, all you have to do is that you look at this lepton number current, you put that into a triangle diagram. Two other vertices attached to W boson, SU2 gauge field, and then you find this anomaly. And the lepton number current coupled to W boson is strictly left-handed. So that's why there's the chiral anomaly for that. Mm-hmm. And the same with the quarks. The quarks that are coupled to SU2 gauge field is strictly, again, left-handed. So again, there's a chiral anomaly associated with that. And if you do go ahead and do the computation, they come with the same amount. So the baryon number and lepton number both are broken by the anomaly. So by the dynamics of this SU2 gauge field, you can change both lepton number and baryon number by the same amount, which is this sticking out the negative energy state. So you change the lepton number, you change the quark number for each color by the same amount, and each quark carries baryon number 1/3. The sum of them becomes 1. So you end up changing lepton and baryon number by the same amount. So then the rest is just looking for the equilibrium. So because now lepton and baryon number can go back and forth to each other, keeping lepton number only without baryon number is energetically not favorable. Trying to balance lepton and baryon number out to sort of make it more even is the minimum of the free energy, and therefore you end up having both lepton and baryon number at the end of the day due to this anomaly process. So all you need to do is to implant the lepton asymmetry at the beginning, then the standard model would automatically balance it out between the baryon and lepton numbers, and that's at least one way we can explain the origin of the asymmetry between matter and antimatter in the universe today.
Okay. Yeah, I think I need to understand what the at a high level it makes sense, but I think I don't know the standard model well enough actually.
Yeah.
I fully appreciate it.
Okay. So I have to delegate the standard model to Lawrence Hall because it's not a course in standard model, it's a course in quantum field theory. So, but I have to finish up discussion anomaly. And so we talked about good anomalies. So the anomaly helped us understand U1 problem, helped understand why pi naught decays, and it might also help us understand why we exist at all. So these are the good examples of anomalies, but they're also bad guys too. And the bad guys appear when you consider chiral gauge theories, and the standard model being one of them. So the chiral gauge theory means that left-handed fermions and right-handed fermions couple differently to the gauge symmetry. And the way the anomaly can actually make the theory inconsistent is by looking at this, again, analog Maxwell equation for the non-abelian gauge field. So d mu f mu nu is the divergence of the field strength and has to be given by the source, which is the current of the fermions. But when you take yet another divergence with the covariant derivative, and using the fact that f mu nu is a commutator between two covariant derivatives, and if you use the Jacobi identity multiple times, it's easy to show that this is supposed to vanish. So if the divergence of the left-hand side vanishes, the divergence of the right-hand side also needs to vanish, and that's this equation. But now this starts looking familiar. We're talking about divergence of the fermion current. So if this divergence of fermion current doesn't vanish because of the anomaly, then the theory is no longer consistent, which means the gauge invariance is lost. And that would be really, really bad. And so if we actually go ahead and compute a triangle diagram with this source current of the fermion to the gauge field, which you stick in over here, and then you have two more powers of the gauge field in this triangle diagram, then I need to use one generator here, another there, a third one there. So the whole diagram will be proportional to this group theory factor of 3 generators. And you have to symmetrize two bosons. So this has to be a symmetric product. That's why there's an anti-commutator. So end result is proportional to this combination of generators called DABC, which is called anomaly coefficient. And if you just go ahead and compute this triangle diagram, you do find, in general, that this current is no longer conserved because of this anomaly, proportional to the symmetric product of generators inside TA, A, and A over there. And so that would actually make the theory inconsistent. So this is a bad anomaly because once gauge invariance is lost, then you don't remove the redundancy in description anymore. So your theory would contain unphysical degrees of freedom that would screw up the unitarity, would screw up renormalizability. Everything goes haywire. So this is exactly what we don't want. That's why this is the bad guy. Any questions about this slide? Okay, so what we need in the end is that you need to have combination of different fermions in such a way that the total divergence would cancel among each other. And the way the anomaly actually arises, again, has to do with the topology too. And here I have to be rather brief because I'm running out of time. So in this case, I consider four-dimensional space-time to be compactified as a four-dimensional sphere. And then you are talking about the gauge group, where four-dimensional sphere is mapped into the gauge group, G. And inside the possible space of all possible gauge transformations, which is already a huge group, which corresponds to every possible map from S4 to G, you can define a loop in that space, which roughly speaking corresponds to S4 times the loop, which can deform into S5. Therefore, this loop can be classified according to the higher homotopy group of a four-dimensional sphere going into the gauge group. So let's imagine that this is that loop which corresponds to this non-trivial gauge transformation. And starting with no gauge field in the middle, and I can define a disk where this loop has this gauge transformation all the way around, and you fill in the blank to make it continuous disk. Then I can consider the determinant of the Dirac operator, namely the path integral of the fermion, as a function on this disk. And if the theory is gauge invariant, because a point along this loop is related by gauge transformation, this determinant should not change. But it turns out that this determinant changes by a phase around by 2 pi, so that you cannot shrink it to trivial as a function of the disk. And the way you see it is that this is what you start with is this the Chern character in 6 dimensions, because we're talking about 4-dimensional space-time and these two parameters. And that is supposed to integrate to 1, or integer in general. And you rewrite this Chern character in terms of diversion of Chern-Simons, so that this Chern-Simons now lives on the boundary, which is nothing but this loop. But along this loop, every point was supposed to be related by the gauge transformation. So if you specialize this loop to be just collection of gauge transformation, you can show that this way of moving only gives you a change in Chern-Simons, again, by yet another total derivative. So the 5-dimensional Chern-Simons is now a total derivative. So what is differentiated is now becomes a 4-dimensional object. And that 4-dimensional object tells you how much the phase of this Dirac determinant changes as you move around this loop. And because it moves around by an integer number, you cannot make it trivial, because it has the winding number again in phase. So this is the way you can also trace the topological origin of this bad anomaly that breaks the gauge invariance. And I realize that I'm going fast here, but any questions about this? So because it has topological origin, you cannot just deny it. It's there. And the way things still work in the standard model is the standard model has many fermion fields according to this SU3 equals SU2 equals U1 gauge groups. And all of these gauge fermions have rather different quantum numbers. And in particular, the left-handed quark is doublet under SU2, while right-handed ones are singlet, and they have different U1 charges and so on. So the table of quantum numbers is fairly complicated. And then you have U1 gauge field, SU2 gauge field, and SU3 gauge field. And there's a Higgs we discovered. Graviton is the only one that we haven't discovered yet. But the point here is that if you look at this table of fermions, each one of them actually gives you anomaly, but they cancel against each other. And you have to check all of these conditions. U1 cube, U1 gravity is also relevant for anomaly. U1 SU2, SU3, SU3 cube, and all these things have to vanish. And there's one anomaly Pleshkin-Schroeder doesn't talk about, namely that just having one doublet of SU2 is also anomalous. And there's a slide on that later on. So you have to make sure that the number of doublets is even. And it is indeed even, because one doublet lepton and 3 colors of quark doublets in a given generation, 3 plus 1 is 4, that's even. So all of these things cancel at the end of the day, and so that the standard model is still a consistent theory. Despite individual fermions giving anomalies, the grand sum of all the anomalies cancel and vanish. So this is the SU2 case. And in the case of SU2 gauge theory, the SU2 gauge group can wrap around in four-dimensional space, S4, in a rather non-trivial way, which has a Z2 classes. So if you have winding number 2, you can actually unwind it. And so because if you do it twice, it unwinds, you can have an anomaly where you have Dirac determinant, and if you gauge transformation, it could change its sign. So that if you do it twice, it returns the original sign. But this is already anomaly in the sense that the Dirac determinant is no longer invariant the gauge transformation because it changed its sign. So that's why you need to have even number of the SU2 doublets so that you get this sign even times, and therefore your fermion path integral is gauge invariant. And this is the anomaly you do not see in perturbation theory, so this is actually non-perturbative. And the same can be said about the three-dimensional theory for all gauge groups. And this is the last slide I'm going to stop here, called Parity anomaly. So 2 plus 1 dimensional fermion is actually anomalous. It violates gauge invariance, but it's, again, even odd thing. And you can see this by looking at the Pauli velocity regulator under parity. So fermion field in 3 dimension would transform this way under parity, and you can check that the mass term is actually odd under parity. So if you introduce Pauli velocity field to regulate the theory, you need to add a big mass term to it. So the theory is no longer parity invariant. So given parity is violated, you can use the epsilon tensor. So when you integrate out the Pauli velocity field, you end up inducing Chern-Simons term. In 2 plus 1 dimension, Chern-Simons term, which is 3 form, can be part of your Lagrangian actually. And then your theory loses gauge invariance again. But if you have even number of them, then Chern-Simons terms become integer multiple, and then hence becomes gauge invariant. And this is the reason it is believed that when you have the condensed matter system in 2 plus 1 dimension, you need to have even number of Dirac points to maintain the gauge invariance of the theory. So again, anomaly has some consequence on the systems in the real world. So, admittedly, I went fast towards the end, but this is how I'd like to conclude the discussion on the anomaly. And then the next week, we will move into the Higgs mechanism. Okay, any questions?
I'm not familiar with the terminology here. What do you mean by Dirac points?
Dirac points is where the fermion energy goes to 0 as a function of somewhere in a momentum space. And they are called Dirac points in condensed matter physics because around those points, you can approximate the relationship between energy and momentum to be linear because it vanishes. So relativistic Dirac fermion becomes a good description around those special points in momentum space, even though you're looking at non-relativistic condensed matter systems. So that's why the relativistic quantum field theory is useful in describing the condensed matter systems, and the impact of anomaly appears in exactly the same way in relativistic quantum field theory versus condensed matter systems.
Thanks.
Okay, any further questions?
So the anomalies, you can know the anomalies cancel exactly because individually the axial current violations all come from these topological effects. Is that right?
Can you say that again?
So to show for the cancellation of the anomalies in the standard model, all of those individually are exact because they come from a topological.
That's right.
So you can know that they cancel exactly.
Right. Exactly. Yeah. So once you check all these equations, even though this calculation is done at the one loop level triangle diagram, this cancellation would persist to all ordinance perturbation theory.
Okay.
That's a good question. Any other questions? Okay. So I see you later at 5 p.m. at discussion section.
Thank you.
All right. Bye for now.